Okay, so greetings everyone. I'm Doc Angelo Arguson, and today's session I'm going to discuss the module number 6 entitled Transform and Conquer Algorithm. So for today's session, our objectives are listed as follows. Okay, so first is we're going to define the transform and conquer, which is actually the core topic of today's session, and we'll be able to discuss the other transform and conquer techniques. Primarily, we have pre-sorting, Gaussian elimination, and balanced search trees. So for the transform and conquer, okay, the main idea of the transform and conquer deals with a group of design methods based on transformation. So in order for us to really understand how transform and conquer works, let us see how the stages, okay, are being laid out to follow through the algorithm. So first, in the transformation stage, the problem's instance is modified to be, for one reason or another, more amenable to a certain solution. Then in the second or conquering stage, it is being solved. As we can see on the image, okay, on our right side, that image explains the three major variations of the transform and conquer strategy in problem solving. So first is we have the transformation to a simpler or more convenience instance of the same problem, which is also known as the instance simplification. Okay. Um, let's try to delve into this first variation. Okay. So the transform to a simpler or more convenience instance of the same problem, or also known as instance simplification, involves transforming a given problem into a simpler or more manageable instance of the same problem. Now, the goal is definitely to reduce the complexity of the original problem by breaking down into smaller, more manageable parts. This is somewhat similar to what you have learned from the divide and conquer. But this approach often makes it easier to find the solution. Okay, so instance instance simplification is definitely to be discussed on our next slide. Okay, but we're going to start discussing the other two for now. Um, transform on a different to a different representation of the same instance, or also known as representation change. Okay. The representation change involves transforming a problem into a different representation, or a kind of format that makes it easier to understand and solve. The core idea of this definitely is that the problem remains the same, but by changing its form or viewpoint, you might discover a more straightforward solution. Okay. To give an example, let's say we consider the problem of finding the shortest path in a graph. Okay, instead of dealing with the graph directly, you might represent it as an adjacent matrix, where each entry indicates the presence of a weight and even an edge, okay? A weight of an edge. So this matrix representation can make it easier to apply certain algorithms like, for example, the Floyd-Warshall algorithm, but still not covered in this slide. The other one is the third variation is also called as the transformation to an instance of a different problem for which an algorithm is already available, or also known as the problem reduction. The problem reduction involves transforming a given problem into an instance of a different problem that has known solution. Okay, that has a known solution. So by leveraging existing algorithms or techniques for the new problem, you can solve the original problem more efficiently. For example, One classic example is the reduction of the traveling salesman problem, okay, to um, to a minimum spanning tree problem. So while TSP or traveling salesman problem is notoriously difficult to solve, finding an MST or minimum spanning tree is more manageable. So by converting the TSP into an MST problem and using algorithms like Kruskal or Prim's algorithm, you can approximate a solution for a TSP. Now let's delve more on the first one, okay? The instant simplification that is actually known for pre-sorting. So what's the main idea of this? Okay. The main idea is that many problems involving list are easier when list is sorted. Like for example, this will help us for searching, or maybe we can have it better for computing the median, where we need where we apply some selection problem, or also when we do check if all elements are distinct or element uniqueness. These things is actually what you can actually encounter when you are using distinct in SQL statements, right? You will definitely have a distinct record to be seen on to the screen if you're using the distinct in your query. Also, the main idea is also to have topological sorting, okay, help solving some problems for DAG or direct acyclic graphs. Okay. You also take note that pre-sorting is used in many geometric algorithms, and that instant simplification is much more needed. So with that, okay, the efficiency of sorting is listed as follows. Okay, the efficiency of pre-sorts depends on the efficiency of sorting, which means that if you have a lot of elements that needs to be sorted, that depends or proportionally, okay, dependent on how the efficiency will be measured. Next, the logarithm of 2 times n factorial is equals to n times logarithm 2 times n comparisons are necessary in the worst case to sort a list of size n, okay, by any comparison-based algorithm. Note about the n times logarithm of 2 times n comparisons are also sufficient to sort the array size of n, particularly popularized by merge sort and quicksort. So next, searching with pre-sorting. Let's say, for example, we have a problem here that we have to search for a given key named as letter K in an array named A, having an element of 0 up until to the positive value of input, okay, -1. So pre-sorting based algorithm could definitely start by stage number one, sort the array first by an efficient sorting algorithm. Okay. Only then you can apply number two, the binary search. Okay. And the efficiency, okay, is actually listed on our screen. Okay. About how this pre-sorting works. So if we are about to do linear search without pre-sorting, definitely we'll be able to have a different efficiency, okay, value compared to a pre-sorted one. Next, element uniqueness with pre-sorting. Okay? Let's say we have another problem here. Okay? Are all elements of an array unique? Okay? If they are, or regardless of the answer is, okay, if we are about to use brute force, we will be able to compare all the elements to each other, right? Or to a certain key. Only then we can be able to solve the problem. Okay. The efficiency is, as we can recall, is O of n of 2. Okay, which is dependent on what? Dependent on the number of elements and and also in the input in this case. So the pre-sorting based algorithm for this will be sort by, again, sorting algorithm. In this case, let's say, for example, a merge sort. And then only then we can scan your array to check pairs of adjacent elements, which is definitely the element right next to the other one or to the key. And another one is when we do compute a mode with a pre-sorted a element. Okay. So by definition, a mode is a value that occurs most often in a given list of numbers. For example, here we have 2, 6, 7, 8, 6, 1, 6, 3, 6, 2. Given with that list, okay, the mode is obviously number 6 because it was the very most or very often being seen onto that list. So if we are about to use brute force to be able to check the most frequent numbers showing up on that list, we will check the frequency of that occurrence of each element and select the element with the highest frequency. Okay. Next, the other implementation, okay, is through the other implementation for matrices. So what we have seen from a while ago is an implementation that can only be applied for a problem that can only be applied for a list. What about if it's a matrix that we are about to solve? Okay, this is where the Gaussian elimination comes in. Okay, Gaussian elimination is also known as a row reduction. It is an algorithm in linear algebra for solving a system of linear equations. It is usually understood as a sequence of operations performed on the corresponding matrix of coefficient. So this method can be used to find the rank of a matrix, to calculate the determinant, okay, of a matrix, and be able to calculate the inverse of an invertible square matrix. This method is popularized by Carl Friedrich Gauss. Okay. Back in his days, okay, some special case of the method they presented without proof were known to Chinese mathematicians as early as circa 179 CE. Now, to continue with, in order for us to be able to perform how this Gaussian really works, you'll need to perform a row reduction on a matrix. One uses a sequence of elementary row operations to modify the matrix until the lower left, again, lower left, okay, lower left-hand corner of the matrix is filled with zeros. So as much as possible. So that's the main goal. You'll have to fill the lower left corner of that matrix, okay, with zeros. So as much as possible. So there are three types of elementary row operations, okay. We have we can do swapping of two rows. We can actually multiply a row with a non-zero number. We can actually add a multiple of one row to another row. Okay. And even if you try to look at other references, there are other techniques, okay, that you can actually use for row operations. Okay. Just to ensure that when you perform this operation, it will still end up with a zero onto the lower left-hand corner of a certain matrix. So using these operations, a matrix can always be transformed into an upper triangular matrix. And in fact, one that is in row echelon form. Once all the leading coefficients, okay, the leftmost of a non-zero entry in each row are 1, and every column containing a leading coefficient has zeros elsewhere, then the matrix is said to be in a reduced row echelon form. So again, okay, every column containing a leading coefficient has zeros elsewhere. Okay. So the final form is unique. In other words, it is independent of the sequence of row operation used. For example, the following sequence of row operations, okay, the third and the fourth matrices are the ones in the row echelon form, and the final matrix is the unique reduced echelon form. So to give you a good example, here we have a certain example. Okay? Using the row operations to convert a matrix to reduce echelon form, sometimes Gaussian. Some authors use the term Gaussian elimination to the process until it has reached an upper triangular or row echelon form. For computational reasons, when solving systems of linear equations, it is sometimes preferable to stop row operation before the matrix is completely reduced. Okay, so you may also ask, why is there a need for transform in Gaussian elimination, you ask? Okay. The matrix with zeros in the lower triangle is easier to solve. Okay, that is the reason. So we can solve the last equation first, substitute into the second, to the last, etc. So working our way back to the first one, the transformation process in Gaussian elimination even simplifies a complex system of linear equations, making it possible to solve them efficiently and accurately. In our case, in order for us to be able to understand this, okay, this happens to be coming from a certain equation where we extract all the coefficient that ends up with this. So for example, we're done with the extraction and it becomes like this. It was being transformed into this matrix. Okay. So we now have three rows: 1, 3, 1, 9, 1, 1, -1, and 1, 3, 11, 5, and 35. In order for us to be able to have this lower left filled with zeros as being mentioned from the previous slide, that's our goal. We need to do some elementary operations, right? Okay. So in order for us to come up with this, okay, I have prepared, okay, an Excel equation so that we'll be able to follow through with this. But before I show that, let's think about it in this way first before we can see the zeros on the lower left, okay? So we have the 1, 3, 1, and 9, 1, 9 at the first row. That will be remain untouched because the lower left zeros are our goal to be transformed into zeros, okay? Whatever that value is. So it turns out to be coming from 1, 1, -1, and 1, okay? In order for us to make this with zero, you have to think of an operation that will make this zero, right? Maybe you can think of this one minus 1 will definitely make it a zero. The same can be done onto the adjacent elements in the same row if you happen to do that onto the first one. So if we do -1 here, that will turn out to be 0. -1 here will turn this um, zero, but in this case, that's not the case. Okay, it's -2 and then -2. So you might be thinking, what would be the operation that they did, okay, onto this second row? So let me show you on our Excel. Okay, I have prepared here some methods that you can do. It's only not limited with deduction, but you have to consider the other rows for you to be able to successfully um, reduce it into zero. So this time, okay, from the original value, okay, we will have to turn it this way. Okay, so first is we have to bring down or copy this first row, and then from here we'll need to think of the operation that we can do, okay, to make it a 0, -2, -2, and -8, because that is our what we have seen from the PowerPoint. But what did they do is that they tried to subtract it with another row. So whatever this value is, okay, this was what subtracted with this one, okay, before it has been or multiplied with the row. So in this case, you can see here on my uh, formula, okay, that I multiplied whatever this first row has, multiply it by a -1, and then So this one, okay, is affected by a -1, then plus by, then you have to add it with this second row, which is actually what we have on to this method. The result of this subtracting your row number 2 with your row number 1. Okay. But we'll have to make sure that we multiply it, right? So that it will still be applicable onto the other one that will result in -2, -2, and -8. Now we also have we have mentioned here the method for 0, 2, 2, and 8 here. For the third row, in order for it to turn into 0, 2, 2, and 8, we'll have to multiply it by -3, because definitely we see that this is number 3. We'll have to make it 0, however, whatever it takes, before we will be able uh, to be able to use on some other rows. In this case, row number 1. Okay, so multiplied with -3 and then add the value of that the third row. So in here, we have um, B7, the first row, okay, times -3 plus B5 or itself. So in here we have 0, the same formula, okay? This, okay, will be the first row times -3 once again, plus its third row, the original one. So it will turn out to be number 2 here. So with this, we were able to have our goal to have 0 and 0 as our lower left, okay, corner. Now next is what we have onto that slide. Okay, we have 0, 0, 0, 0 here. This will be able to have a value filled with zeros. So we also have it a comment here on our how we will be able to do that. Okay, so we will bring down the first row again. Okay, remember that this remain untouched. Okay, for the second iteration, we will be able to divide the row number 2, this row number 2 by -2. So in this case, since we know that this is -2, this is -2, and this is -8, in order for it to be to reduce, we'll have to divide it by 2. So we now have 0, 1, 1, and 4. You can see it on my equation here. Next, this turns out to be zeros, okay, now, because we subtract it twice with our row number 3 with our 2. Okay, so how do we do that? Okay, by following the third row to be subtracted twice by the second row. So if this is our B12, this is now our new second row. Okay, that will not be used as a reference anymore. Whatever we have here, okay, it will be subtracted by the second row. Why? Because if you happen to notice, we have this 2, 2. In order for it to become 0, we'll have to deal with the -2, right? With the adjacent row right next to you. And then it will also be affected by the other one. Notice that since we now have 4 in here, okay, we now have 0 on to this row by following that rule. So again, this is one of the things that you might be able to learn from Gaussian elimination. Okay. So next, again, this only applies on matrix or matrix problems. Next, let's move back to the slide. Okay. So until you will be able to solve it like this, okay, you will now have 1, 0, -2 and 3. This time, we were able to at least have a 0 here, okay, and a letter L shape of zeros here. Okay. So I will leave the history reading for you. I'm not going to read that because I'm after here for the discussion of how the algorithm works. Okay. Regarding with the regarding with the Gaussian elimination, okay, how it works. Okay, I also have another example here that you can follow through. Okay, so with this, this will be easier for you if you try to put put some time on reading this slide. Okay. So next, the other one is implementation of instant simplification to a balanced search trees. Okay. So we're done with the implementation of it on a list, then on a matrix. Now we implement it on a tree. Okay. In computer science, the AVL, okay, or Adelson-Valsky Landis tree is a self-balancing binary search tree. So we haven't had a discussion of this kind of search tree before, but this is now our chance to be able to do so. It was the first such data structure to be invented. In an AVL tree, the heights of the two child subtrees of any node differ by at most 1. If at any time they differ by more than 1, rebalancing is done to restore this property. Lookup, insertion, and deletion all takes big O of logarithm of n time in both the average and worst cases. Okay, where n is the number of nodes in your tree prior to a certain operation. Insertions and deletions may require the tree to rebalance by one or more tree rotations. So in this discussion, you'll be able to be introduced. Okay, you will be introduced with terminologies such as rotations and balancing of a certain tree. So I will leave this part, again, the history to you, but this is definitely expected to be part of your formative or summative assessment. Okay. So I'm going to discuss again what is definitely the gist of the topic. Okay. Which is definitely the discussion of how it works. So here we see the first three is balanced and the next two are not balanced. This is the first one, balanced and not balanced. Okay. Balanced because we do have left and right nodes on it. While when we say not balanced, we don't have the other counterpart on the other sides. Okay. So in the second tree, which is this one, the left subtree C, okay, has a height of 2. 0, 1, 2. That's number 2. Okay. And the right subtree has a height of 0. Okay. So the difference is definitely 2. In the third tree, the right subtree of A, okay, has a height of 2, and the left is missing. So it is at the so it is 0. Okay. And the difference is 2 again. The AVL3 permits this difference to be only 1. Okay. So that we can use a balance tree. Okay. So the valence factor is computed as follows. Okay. Valence factor for this one to happen is equals to a height of your left subtree minus the height of a right subtree. Okay. So if we have the left subtree equal to each other to the right side, definitely we'll get a 0. Okay. Then that would mean a valence factor. So if the difference in the height of the left subtree is more than 1, then the valence is using some rotation techniques. So the AVL rotation to balance itself, an AVL may perform the following 4 kinds of rotations. The AVL might do left rotation, right rotation, or a combination of both, left right or right left rotation. The first two, okay, The first two identified in these listings are single rotations. Take note that it's only single, and then the next two rotations, combination of left, right, or right, left, okay, are double rotation. So it's easy to understand in that way. Okay. So to have an unbalanced tree, we at least need a height of a 3 by 2. And with this simple tree, let's try to understand them one by one. Okay. Let's understand how the left rotation works. Okay. If a tree becomes unbalanced, okay, like this, when a node is inserted into the right subtree of the right subtree, then we perform a single rotation. Okay, so again, when that happens, okay. So in our example, the node A, this is happens to be the letter A, become unbalanced as the node is inserted at the right subtree. So if we are about to balance things out, there should be that letter C should be added here, not here onto the right side of letter B. So we perform the left rotation by making A the left subtree of your B. In this case, let's take a look. First, this is the stage one, okay, and then we rotate, okay, to the left. This time we will be having our letter B to become our root node and our A and C, okay, as our node, okay, or the child node of letter B. So again, we only use a single time rotation in this case. And that makes the left rotation matters for this example. On the other hand, this is actually how the right rotation works. Okay? As depicted, the unbalanced node becomes the right child of its left child by performing a right notation. So this happens to be our scenario. Okay, let's take a look closer. So 0, 1, 2, letter Z is at the topmost. We will rotate to the right. Okay, and since we said right, the element on the right should be rotating to become a subtree, or I mean a node. Okay, a child node of the one in the middle. Next, the other one is somewhat tricky. Okay, the left-right combination or the right-left rotation. This means that we'll do rotations twice. Okay, double rotations are slightly complex version of an already explained version of rotations. Okay, to understand them better, let's first check how to perform the left-right rotation. Okay, in this case, we will have to look at it step by step. Okay, on stage number one, the letter A node has been inserted to the right, uh, into the right subtree, okay, of the left subtree, which makes definitely the C an unbalanced node. Okay, the scenarios can cause the AVL tree to perform the left-right rotation. First, we perform the left rotation onto the left subtree of C. This makes letter A the left of subtree B. So in this case, it has to be the left. Again, this is called left then right rotation. So we use left first, okay, onto this stage. Next, the node C is still unbalanced even if we tried doing the rotation. However, it is because of the left subtree of the left subtree. Okay. Next, we shall now rotate to the rotate the tree, okay, by solving this issue. So making your B the new root node of the subtree C. Okay. Remember, this is just a subtree. So we are expecting another tree, okay, to be added here, but it's not actually happening in this case. So we need to make sure that this subtree will turn out to be a tree on itself. So we're going to tweak this, okay, letter C by rotating it to the right. So C now becomes the right subtree of its own left subtree. So the tree now is balanced, although it started as a left subtree. Okay. okay? Because we might be expecting some other nodes here, but it's not being shown here. So we expect an A, and B, and if ever, there should be a certain um, node here. But in this case, for the sake of discussion, it was only shown at 3 so that we can perfectly perform a left-right rotation. Next, we move on to the next rotation, the combination of right to the left. Okay? Just as what we have learned from the left, right, okay? This time we'll need to rotate first to the right, then to the left. Okay, so this is the current state or the initial pattern or state that we are having. Okay, the pattern that we will modify later. Okay, a node has been inserted to the left subtree of the right subtree. So this is the right subtree, and there's a left subtree being added. This makes your A an unbalanced node with a valence factor of 2, 0, 1, 2. First, we perform the right rotation along C node. Okay, this along with the C node will rotate B the middle and C onto the right. Okay, so the node A is still unbalanced. Okay, and still since it's unbalanced, we'll need to do some rotation. Okay, a left rotation is performed here so that we can make our B our root node. Okay, having our A be planted somewhere onto the left side of the root node B. This will definitely result in what you have seen onto the screen. Okay, the tree will become like this. Okay, so I hope that works better. Okay, when it comes to the rotation. Okay, next. Okay, complexities of different operations on an AVL tree. Okay, so you can see on our screen there's actually a table about insertion logarithms compared with the deletion and search logarithms. So how do they differ now? Okay, definitely at insertion, the time complexity for inserting an element into an AVL tree is O of logarithm of n. Okay, and this is definitely because the AVL tree maintains its balance property, ensuring that the height of the tree is logarithmic in relation to the number of elements in a tree. And on to the deletion, okay, the time complexity for deleting an element from an AVL tree is also O of logarithm of n. Okay, this is similar to insertion, since that the AVL tree ensures that the tree remains balanced after deletion, resulting in logarithmic time complexity. And search. Okay. The time complexity for searching an element in AVL tree is also a big O of logarithm of n. Okay. Since the AVL tree is balanced, the search operation can be performed efficiently within logarithmic time. Next, moving on. Okay, AVL tree application. So this can also be applied for indexing large records in your database because AVL trees are used to efficiently index and manage large data sets in databases. Due to their self-balancing nature, AVL trees ensure that operations like insertion, deletion, and search remain efficient, typically with the time complexity of O of logarithm n. So this makes them suitable for handling large volumes of records where quick data retrieval and updates are critical. AVL3 is also applied in searching in large databases. Okay. AVL trees are employed for searching large databases because their balanced nature structure allows for fast search operations, ensuring that the queries can be executed quickly and accurately. This is especially important in applications where the speed of a data retrieval impacts the overall performance, such as in in search engines and large-scale data analytics. For the program implementation of ABL3 or source code, I will leave it up to your laboratory for you to be able to try the codes and be able to learn from them. I hope your professor for laboratory will be able to explain this with you or be able to give you a rundown about what this program means and be able for you to how did you will be able to come up with your output. Okay. So with that, I end my discussion. Thank you very much for listening. I'm Dr. Angelo Arguson, and I'm signing off.